Okay, so in this video we're going to start talking about topic 4. Specifically, the first unit we're going to be focusing on is 4.1, and you should have already watched your introduction videos to this topic that kind of talk about different types of oscillations and where they occur in nature. And the second video was about simple harmonic motion and how that arises for a mass on a spring. And so that's kind of what we're going to start with today. Simple harmonic motion is basically the, I guess it's in the name, by definition it's the simplest type of oscillation an object can have. And when I say oscillation, I just mean like a back and forth type of motion. Now, by definition, simple harmonic motion occurs when what's called a restoring force causes an object's acceleration to be proportional to the object's displacement from equilibrium and in the opposite direction of that displacement. And as we go through this first example, you'll see at least one situation where that can arise. Now, the reason we talk about simple harmonic motion, even though it's not super realistic, is because like most things we learn about in physics, we start with the more basic type of motion, and then we can talk about more complicated types of motion later on. Simple harmonic motion can actually be used to approximate many situations that are actually more complicated. Anything from a bottle floating in the ocean, bobbing up and down, to a pendulum on a grandfather clock swinging back and forth. If you imagine dropping a marble in a spherical bowl and having it roll back and forth and back and forth, or even something more complicated like two molecules interacting each other. Like when we talk later about greenhouse gases, we can see that you can even model greenhouse molecules as particles connected by a spring that oscillates back and forth. And so the concepts of simple harmonic motion can be applied to more complicated situations, which is why it's worth learning about them first. Okay, so that's basically why we care about simple harmonic motion. Okay, now the example we're going to start with is just one example of how simple harmonic motion can arise. Remember, going back to the definition of simple harmonic motion, you get this type of motion when you have, number one, a restoring force that causes an object's acceleration to be proportional to the object's displacement from equilibrium. This right here is like the first requirement for simple harmonic motion. And then the second is that acceleration or that restoring force has to be in the opposite direction of that displacement. And so any situation where we get those two conditions met, we can get simple harmonic motion. And so the example I'm going to give you with the mass on a spring is only one out of many, many, many different examples where you can have a situation where those things are true. Okay, so let's talk about a mass on a spring. Okay, so the scenario we're going to start with is, let's say you have a mass attached to a horizontal spring, and let's say that the spring is free to oscillate. And just to show you what I'm talking about a situation like this. Okay, I would try drawing this myself, but I promise my picture would not look so nice. Okay, so we're basically assuming we have like a box or some type of object on a surface here, and it's attached to the spring, and the spring is free to oscillate back and forth, kind of like you see in this animation here on the right. And we're going to assume that there's no friction, there's no air resistance or anything like that in the situation. And what we're going to do is we're going to apply Newton's second law to this situation, and we'll see that through Newton's second law, you can basically get to an equation that lets you know that you've met the condition for simple harmonic motion. Okay, so let's start with this picture right here. I'm going to take this picture and I'm going to make it bigger. Okay, because otherwise I would have to draw it myself, and I'm not that good at drawing. Okay, so here is the setup. So let's say we have a mass attached to a spring, like you see right here, and let's say that this box on the floor is just sitting there on the floor, and let's say that so let's assume that we take this box that's currently at rest. This is what we normally call the equilibrium position. Okay, so this is the object's natural position. We'll call this equilibrium. Okay, so this is the equilibrium position, and we will call this x equals 0. Okay, we have our coordinate system, and we say that x is equal to 0 at this point. And then let's say we take this box and we pull the spring out. Okay, we stretch the spring out over here so that the box is now moved to the right. Okay, I could have started by pushing the spring in, but it doesn't really matter. And so now the spring is at a new position, and that new position is what we're going to call x. Okay, and x is what's called the displacement from equilibrium. A displacement from equilibrium. It's literally how far the object is from its equilibrium position. And displacement from equilibrium is a vector. And so in this case, it would be pointing to the right because the spring was pulled out to the right. If you had pushed the spring in, then it would be pointing to the left. Okay, so displacement from equilibrium, that is what x is. Now, we have not spent a lot of time talking about springs. But springs, at least some springs, obey what's called Hooke's law. And I'm just going to go to next slide really quickly so you can see the next slide of notes. Okay, if you want to try to add this to your notes, I know there's a picture covering it up, but I don't want to erase a picture yet. Okay, but if you want to add this to your notes. Okay, so basically what Hooke's law says is that if you have a spring, an ideal spring, then the force exerted by the spring is directly proportional to the displacement of the spring from its equilibrium position and in the opposite direction of that displacement. Now, here's what that means. Okay, the force from the spring, I'm going to write Fs, or maybe I'll just write F spring, is number one, proportional to the displacement from equilibrium. So if you don't know what proportional means, mathematically speaking, a proportional relationship basically looks like you have some constant times a variable. So if I have a spring force that is proportional to the displacement from equilibrium x, I can write it like this, where k is a constant. Okay, and that is what a proportional relationship would look like. If you were to graph like spring force on the y-axis and displacement on the x-axis, then this would be basically like a linear relationship. Okay, so a proportional relationship is a special type of linear relationship where there's basically no y-intercept. In other words, if I double x, the spring force also doubles. If I triple x, the spring force also triples. Okay. Hooke's law says that the force from the spring is proportional to the displacement from equilibrium and in the opposite direction of that displacement. And so actually we need to add a minus sign here to indicate the direction. In other words, when x is positive, like here in this picture, x is positive because it's being pulled out to the right, the spring force would be going in the opposite direction. So here, the way I've drawn this, the spring force would be going to the left. Okay, if I had pushed the spring in instead of pulled it out to begin with, then the displacement would be to the left and the spring force would be to the right. In other words, the spring force is always pointing towards equilibrium. And intuitively that probably makes sense because we all know if we pull a spring out, then the force from the spring is going to like pull it back in and vice versa. Okay, so this is what's called a restoring force because it's basically the force is always pointing towards equilibrium. Right, and it just so happens that many springs obey Hooke's law, and so many springs have a force that is given by Hooke's law, which is right here. And by the way, this is probably one of the first times we've ever seen a force that is not constant, but that actually changes with position. Okay, so we probably didn't see that in IB Physics 1, but there you go. Now, of course, we know we have the all-powerful Newton's second law. Okay, and in mechanics, everything comes down to Newton's second law, F net equals ma. And so what I'm going to do now is I'm going to apply Newton's second law for my box on a spring that's been pulled out. Okay, so let's say on the right side I have the mass times the acceleration, and then on the left side I have the sum of the forces, but there's only one force in the x direction. Okay, so let's say I'm writing this for the x direction, F net x, max. There's only one force in the x direction, and that is negative kx. Okay. By the way, I don't know if I mentioned this before, but you might recall from IB Physics 1 that k is what's called the spring constant. Okay, that is a constant for a given spring. In this context, the spring constant basically tells you like how stiff the spring is. Okay, so how hard it is to pull the spring back. So some objects have a very high spring constant. For example, like a rat trap probably has a high spring constant. Some springs probably have a very low spring constant, like the spring that's in your pen that you click the top and the pen goes in and out. And so spring constant is just a constant that pertains to a given spring. Okay, but getting back to our second law equation down here, what I want you to see is by applying Newton's second law, we basically get an equation that looks like this. And if I manipulate this just a little bit, okay, if I divide both sides by the mass, okay, then I get that the acceleration is equal to minus kx over m. Now, think back a few minutes ago when we talked about the conditions for simple harmonic motion. Okay, number one, simple harmonic motion occurs when you have a restoring force that causes an acceleration to be proportional to the displacement from equilibrium. Now, this is a proportional relationship as long as whatever is in front of the x is a constant, which in this case it is, because we're assuming that the mass and the mass of the box and the spring constant are constants. Okay, so what I have here is I have the acceleration is equal to a constant times the displacement from equilibrium. That means the first condition for simple harmonic motion has been met. Okay, the second condition was that the direction of that acceleration should be in the opposite direction of the displacement from equilibrium. And that's what that negative sign indicates right there. Okay, it means whatever sign x has, a is going to have the opposite sign. Okay, and so my two conditions for simple harmonic motion have been met. Okay, provided that k over m is a constant. And Walter Lowen talked about this in the second video that you watched. But I realized he might have been going a little quick because it's a college class. Okay, so some of this should hopefully look familiar. Okay, but hopefully what I've convinced you of is by applying Newton's second law to this one situation, we've arrived at a situation where the conditions for simple harmonic motion are met because I have an acceleration that is, number one, proportional to the displacement from equilibrium, and number two, in the opposite direction of that displacement. Now, I haven't told you really what simple harmonic motion is. I've told you what conditions it exists under, but I haven't really told you the properties of simple harmonic motion and what that looks like. Okay, so that's what we're going to talk about now. So pause it there if you need to finish looking at that. Okay, so this is just kind of going through the notes. This we kind of talked about before. I had some people ask me about what the omega in Walter Lowen's video was. And so basically, what you can do is you can write, for the mass in the spring, when you apply Newton's second law, you get negative k over m times x. And what he did in the video was he wrote this k over m, which is just a constant. He just wrote it differently. He called that omega squared, where omega is what's called the angular frequency. Okay, and if you recall back to normal frequency from last year, omega is also 2 pi times the normal frequency, or 2 pi divided by the period. Yeah, those are equations we've seen before back in circular motion. All right, and basically the only reason he did this is to make the constant come out nicely when you apply the calculus and you take the the second derivative of the position function, and just to make everything come out nicely. You don't need to know calculus for this class, and so it's not that crucial necessarily that you understand the calculus behind all of that, but be on the lookout for understanding that this constant is often written as omega squared. And again, that's just a constant, because remember, when you have a proportional relationship like this, you're basically saying acceleration is equal to some constant times x, and in this case they just call the constant omega squared. And then the negative sign indicates that a and x have opposite directions. Okay, so of course we can kind of like visualize what that motion is going to look like. It's going to be some type of back and forth motion, but we'll get more into that as we go through here. Okay, so this is just going back to the mass of the spring. You might sometimes see me write this symbol right here. Okay, is the proportional symbol. So if you ever see this rin, that's basically saying that the acceleration is proportional to negative x. In other words, the acceleration is equal to some constant time, or negative some constant times x. Okay, so that is the proportional symbol, in case you ever see it. Okay, so now let's ask ourselves a little bit more about this motion. So based off of what I've told you about Hooke's law and the spring force, in what situation is the spring force going to be 0? Okay, so the spring force given by Hooke's law, right, is 0 when the displacement is 0. In other words, when the object is passing through equilibrium, right, because x is the displacement from equilibrium, as the object is passing through equilibrium, the spring force is going to be 0. Now, what is the mass going to be doing when the spring force is 0? Is it going to be stopped? Well, no. In fact, it's going to be moving the fastest at its equilibrium position. And so just to go back a few slides to this animation, okay, if you kind of look at the motion of this mass on a spring over here, notice that I can't draw on the slide, unfortunately. Okay, but notice that the equilibrium position is somewhere here in the middle. Okay, there's two endpoints, and then the equilibrium is somewhere in the middle. Okay, and so the spring force is 0 as it passes through equilibrium, because the displacement from equilibrium is 0, but the object is still definitely moving at that point. What does happen is at the endpoints, right, the object does stop moving. Okay, and so putting that all together, let's consider trying to enter the question on this chart, which is basically saying where is the displacement, the velocity, and the acceleration going to be the greatest. Okay, and looking at this picture, we can see that this is basically still the mass of the spring, but it's just a vertical spring rather than a horizontal spring. That doesn't really change anything. Okay, so where is the displacement going to be the greatest? Well, here is the equilibrium point, right? And so the displacement from equilibrium is going to be greatest at C and at A, okay? Because the displacement from equilibrium is 0 at B, because that is the equilibrium point. Okay, now keeping in mind that the acceleration in simple harmonic motion, let me make this a little bit bigger. The acceleration in simple harmonic motion is proportional to the displacement from equilibrium. That basically means that whenever x is at a maximum, the acceleration is also going to be at a maximum. And when a is 0, the acceleration, or the displacement from equilibrium, is also 0. And so acceleration and displacement are also at a maximum at the endpoints. Okay, now what about velocity? Well, the velocity is actually the greatest in the middle. Okay, and there's a few things that there's a few ways to think about why that is, and we'll look at some different ways as far as, you can think of mathematically speaking. You can think of, in terms of energy, kinetic and potential energy, the displacement from equilibrium at position B has no spring potential energy, because remember, spring potential energy, we talked about this in IB Physics 1, but spring potential energy is given by 1/2 kx squared. Okay, and so when x is 0, that is at equilibrium, there is no spring potential energy, and so all the energy in the system is gone into kinetic energy. Okay, so at position B, the object is moving its fastest. Okay, so that's one way to think about that. Okay, now before we get too deep into looking at what the graphs for simple harmonic motion looks like, I do want you to take some notes over some vocabulary terms. Okay, so I'm just going to go through these slides really quickly. I want you to pause and add this to your notes. Okay, so the maximum displacement from equilibrium is what's called the amplitude. That's typically given the symbol capital A. So in the example here, you can see that the amplitude is 0. And by the way, amplitude is not ever a negative value. Okay, it's just the maximum displacement from equilibrium. Okay, that's not a vector, it's just a number. Okay, how far the object can possibly get from equilibrium. That's called the amplitude. Period we've talked about before in the past. That is the time it takes for an object to complete one full oscillation. So one back and forth, that amount of time is called the period. Okay, it's given a capital T and not a lowercase t, because lowercase t is just any old time. Capital T specifically means period. And so if we pull this box out from here, let's say we let it go and we time how long does it take to go, all the way over here and then all the way back, that amount of time would be one period. Okay, and we've seen that terminology before. Okay, we've also seen on the next slide, we've also seen the word frequency before. Okay, frequency is how many oscillations you have per second. Okay, so period is the time for one oscillation. Frequency is how many oscillations you have per second. Okay, and because it's basically the inverse definition of period, frequency is also 1 over the period. Okay, or you could say period is 1 over the frequency, same thing. Period is a unit of time, and so usually it's measured in seconds. Frequency is measured in cycles per second, but the name we give for that unit is called hertz. Okay, Hz. Okay, so 2 hertz would be 2 cycles per second. Okay, so if you know the period, you automatically know the frequency. Okay, and the last thing I want to talk about in this video is what's called phase difference. And then in the next video, we'll look more at the trig functions for simple harmonic motion. Okay, so phase difference basically comes down to what's called initial conditions. Okay, how is the object set into motion? Okay, so for example, if you go back to the mass on the spring example, there's lots of different ways you can get this thing moving. Okay, you can pull it back to the right and let it go, or you could like push it to the left and have it start off going to the left. You could, pull it back and let it go with no velocity, or you can give it a push so it has an initial velocity. Okay, and the initial conditions don't affect the period. Okay, it doesn't really affect how long it takes for the oscillation to happen. All that does is, if you imagine the graph of this, of course we haven't looked in detail about the graph yet, but if you imagine the graph of it, it's going to be some type of trig function. It's going to be like a sine or cosine function. We'll see that in the next video. Okay, the only difference is that based off of where the object starts, it kind of shifts the graph to the left or to the right. Okay, so in this situation, whether I pull the mass out and let it go, or whether I push it in and let it go, it's still going to oscillate back and forth, and the graph is still going to look like a sine or cosine function, but they're going to be what out of sync with each other. Okay, there's going to be what's called a phase difference. And when we talk about a phase difference, that's a terminology that you need to be aware of. Okay, a lot of the time we're talking about the angle between two oscillations. Okay, so a lot of the time phase difference is measured either in angles or in terms of the period. And so, for example, on the next slide, it says two identical mass spring systems are started in two different ways. What is their phase difference? Okay, so the one on the top, the box is pulled out to the right and let go. The one on the bottom, okay, it starts at equilibrium, but it's given an initial push to the left. And so even though I don't want to get too much into the graphs, what the graphs are going to look like, the graph for the top one would look something like this. It would start, at the, wow, that's a terrible graph. Let me try that again. It would start at a positive displacement, and then it would go back down towards equilibrium, something like this. Whereas the box on the right, it's starting at equilibrium. Okay, so it would start here, and then it's traveling to the left, and so it would start off with a negative displacement, and then it would go back up, like so. And so the shapes of these two graphs are very similar. They're just kind of offset from each other. Okay, and the question is asking about the phase difference. And what it means by that is it's basically asking, okay, so if you think about this graph, or if you think about the second graph right here, this second graph is ahead of the first graph by how much? Okay, so the second graph, it starts at 0 and then it goes negative. Okay, this one starts at the maximum displacement and then goes on ahead. Okay, and the way to think about the phase difference, I don't know what the symbol for phase difference is that they use. Phase difference, at a higher level of physics, we would normally write that like with a phi, like this. But the way you would figure it out is you would think in terms of period. Okay, so from here to all the way over here, okay, that is half a period, because one period is one back and forth. Okay, so from here to here would be half of a period. The actual phase difference in the situation is from here to here, which is half of a period. So in other words, I would say that the phase difference is 1/4 of a period. Okay, and depending on how the IB asks that question, either you would answer the question as 1/4 of a period, or you would convert that to an angle in radians. And the way you would do that is just to remember that basically there's 2 pi radians in one period. Okay, so the phase difference, if you wanted to write in terms of angle, you would write like 2 pi over 4, and then you would write pi over 2 radians, and that would be the phase difference, or I guess that would be 90 degrees phase difference. Okay, hopefully they ask you in the question how they want the phase difference written. Sometimes it's in radians, sometimes it's in degrees, sometimes they'll take both. Sometimes it's in terms of the period, like you could just write, t over 4. It just kind of depends on how the question is written. Okay, so that's the idea of the phase difference. It's basically, if you're thinking of the sine and cosine graphs, it's basically talking about like the horizontal shifts between two different oscillations. Okay, and again, that's either in terms of the period or in terms of an angle in radians or degrees. Okay, so I know there is a lot of information in this video. In the next video, we'll take a closer look at what the graphs for simple harmonic motion looks like, and we'll talk about energy considerations in simple harmonic motion, and then after that we will move on to talking about traveling waves. Okay, so as always, please let me know if you have any questions, and I will see you guys in the next video.